我们开始上课。So last time we did an introduction on the field series. I explained why we need the and most of you will not what is field series. After that, we basically do a point out QFP is the result of the mechanics and following this, and the Lorentz transformation basically returns this Lorentz group. So, by looking at how object transform under the Lorentz transformation, basically classify different objects, such as Lorentz scalars, Lorentz vector, and Lorentz tensor. So this is a bit different from the usual leading vector scalar tensor in the sense. This is kind of full vector, and full vector is full vector. We also introduced the calculation rule, some calculation rule involving these objects. For instance, we can do inner product, we can contract the index, things like that, right? So this is something new, and we appear quite often in this course. So the last part of last lecture is we introduced the second. In mechanics, we show how to solve it. The Heisenberg picture, as you can see last time, is pretty simple. Yeah, this is the content of last lecture. Do you have any questions? Okay, now we will continue. So basically, the goal of today's course will be how to complex field. Introduce why we need to complex field. Now, how to do it. So this is the main goal of today's course. But before this, we need a little bit of basic knowledge about the field theory in the classical level. Let's try to start by introducing the classical. Of course, we already know some examples, like Maxwell's theory, Maxwell's equation. It's all about the classical theory. But the goal here, we need to be a little bit systematic to discuss the theory. First of all, we want to define a field theory. What do you mean by a field theory? Field theory is not about something. It's not only about some field. It's a field. So we need to specify the dynamics. What do we mean by a theory? They refer to the dynamics of the field. in classical field theory context, this is defined by problem. All right. We can take this definition, A definition. So the only one is A definition. So our Lagrange will be is a function of the field. It's a function of the field and possibly relative. I thought that here I mean timing. They also involve the special relative. Use gradient operators. Right? You may already know. So this is the analogy of classic mechanics. Rigorous. Lagrange in classic mechanics are similar. So by the Lagrange, we use this capital L. We know from classical mechanics it's a function of time. So since this is the field theory, also involves spectrum. So we also define something called the Lagrange density, which we use this curly L. And as I said, this is a function of phi, the field itself, phi. You can have multiple fields, we might use the additional index to label different fields. By the each sense, it could also depend on the derivative of the phi, including the time and the space derivatives. So, brief the index. You can systematically write in this way, depending on these two objects. Yeah. So this is something called Lagrange density. You can say from many textbook literatures, we basically don't distinguish the Lagrange density and the Lagrange stuff. Sometimes just call this is Lagrange. So this is Lagrange. We know also from mathematical mechanics, the action will be the time interval over the Lagrange. In this case, the additional space interval integrating will be the Lagrange density. So you can take this as a definition for specification for acid abuse. So as you might remember, in classical mechanics, the Lagrange L can only depend, it depends only on, let's say, in classical mechanics, we're usually using Q, P, right? P is conjugated with Q, Q dot, something like that. It's represented as a classical variable, or dynamical variable in classical mechanics, right? So we know that L can depend on Q or Q dot. Okay? But not a double dot. Right? What is the reason for this? What is the reason for this? analyzing something. Because in classical mechanics, the state of an object or degrees of freedom, we want to solve the state, okay? For a classical object, we only need we only need to know the initial condition specified the position and the velocity in order to solve it. Okay. Is that clear? If your series, if your action or Lagrangian depends on Q double dot, which means what? Because the degrees of this differential operator increase, you need more initial conditions in order to get a solution. Right? But we know that's not our word, okay? That's not our word, okay? Or you might argue this could be related to the classical mechanics, something causality or whatever. But yes, we know, yeah, it's very clear the Q double dot is not allowed. So similarly, here, theory, we also restrict to curly L depending only on phi and I dot, but not double dot. It dots mean time invert. Now, this is only about time at this moment. As we learned from last course, last week's course, if we want to maintain Lorentz invariance, Lorentz invariance will require, in some sense, we should treat the space and the time in equal footing, right? Right? With Lorentz invariance. Okay? So, because of, with this Lorentz invariance as the additional constraint, curly L should only depend on phi and the hyperbolic phi, right? But not higher derivatives, okay? But if you're trying to argue, say that I don't want to learn the invariance for some reason, okay? But this is not the topic of this course, but for curiosity. By a priority, we can try to write some theory breaking the Lorentz invariance. Yes, you can do that. Then that constraint only allows the time derivative, and you might want to construct some theory in terms of higher space derivatives of this field. That's perfectly okay. It's just not the topic of this course. So in principle, you could. In principle, the Lagrangian density could depend on higher space derivatives. But if you demand a Lorentz invariance instead, you just use a new index to cover all these four, including time, x, y. Is that clear? Yeah, this is the first restrict, right? Because this form is quite systematic or quite general. Like, keep asking what are the constraints this function should satisfy in order to give a very defined theory, give a definition for the classic theory. Okay? Now, the next step is the important one, which from this given, suppose I want when you give me such kind of theory, I should be able to derive the equation motion. It's like classical mechanics. From a Lagrange, you derive equation motion. So how to derive equation motion? How to derive it? Use the least action principle. When you have to extremize the action, here we do the same thing. In order to derive it, we have to vary the field phi. Let's see. I do a very generic variation of my field phi. Now this phi here should refer to the field. Okay? Sometimes I just drop the index, the space-time index, but you should keep in mind. These are just a field. Just change the field a little bit, okay? Change the field itself a little bit with the most generic way. Generic way means we can do whatever shape changing, okay? So this is not some particular small change. It's a generic small change. Now we try to look at what happened for the action. That's great. So the variation or the change of this action under this change of phi can be expressed because action is a function. Okay? Action is a function of phi. So under this change, the action should change according to some rules. So we write down it. So this change of the action can be expressed as the derivative of the Lagrangian density with respect to phi and the derivative of phi. Right? This is partial by A, delta by A plus right? We just mentioned above the Lagrangian density should be viewed as a function of phi and partial phi. Okay? So when you do a generic variation changing phi, in order to read off how much change the action is changed, you can do this such kind of extension to get the change of the action. Okay? Now you calculate this one by basically combining the first term and the derivative of term combined this way. Right? So we basically realized that if I exchange these two, this is about a derivative only for this term, but not for this. Okay? Okay? Now we can transform this term into a total derivative minus something, right? If this is the single term. If you combine with this term, it forms a total derivative. You see? And this is the derivative of this part. Yeah? Okay? And the remaining thing will be a total derivative. The remaining thing will be a total derivative. So whenever we have a total derivative, since this is the integral, that derivative is precisely with respect to x mu. Right? Now we integrate over. We integrate this x mu. Right? So this term, since it's a total derivative, it becomes a surface term. Surface term means you do the usual integral. When you integrate the object you want to integrate, if it's a derivative, it's a total derivative. After integration, it goes to a surface or boundary term. It goes to a surface term. Surface term means only receive contribution from the boundary. Okay? I impose particular boundary conditions or good boundary conditions. Those terms can be dropped. Dropped means it's zero, just zero. Okay, it's not contribute. Right? For instance, looking from this structure, since the total derivative, the object, the part inside this bracket, okay, will be precisely those surface terms, special surface terms. So either I can choose the boundary condition C, this variation of phi, the field itself. We can set this is equal to 0. This is equal to 0, boundary. Or we can set this one equal to 0 as a boundary. Okay? So just the corresponding to boundary conditions. So sometimes we often refer to this kind of boundary condition as the initial boundary condition. It is the fixed. It's a fixed linear of this boundary condition into what? Then at the boundary, you don't vary the field. Okay? You fix the value of the field at the boundary. That's the meaning of this boundary condition. Right? Now, you can also fix this at the boundary. Set this equal to 0 at the boundary. Of course, you can do that. Okay? The meaning of that is also obvious because this is the object conjugate with this phi. Okay? Okay? Means you fix the conjugate at the boundary to 0. Okay? There are two different boundary conditions. After you impose those, you can safely drop this term. Okay? This is for a general system. System means the field. The system means the field and has a boundary. Okay? If you disregard the boundary, it just means this is you can drop it already. If there's no boundary, it should be 0. Okay? Because it's only receiving contribution from the boundary. So after you impose those, now the remaining part is this one. Now this comes to this important thing. So we basically demand, in order to solve the equation motion, find the equation motion, we demand under arbitrary small change or arbitrary variation of this field. Okay, delta S should be 0. Okay, delta S should be 0, right? That's the extremization condition for the action, for this action condition, right? You see, since this is arbitrary, for arbitrary delta phi, this should always be 0. It just means this coefficient part, okay, is 0. So again, this is equal to 0, this part. This part should be 0. So this is this equation is precisely the equation motion of UI. Okay. The equation motion for the classical field coming from the extremizing the action. Is that clear?
Now, you may don't like a Lagrange description or action language. You might say, okay, I have many different languages in my classical mechanical course, so what are the others descriptions, okay? So how many languages you learned in your classical mechanics? How many? At least you should know there is an accounting description, there is another. This is the two you should know. There are a few more others. We're going to discuss those, just try to mention it was parallel to this part. That's also used here. That's the physical. For instance, I will ask another point for this piece. Again, just go back to a classical mechanics. Just trying to do the experiment. Okay? We know that in the classical mechanics, we define quantitative level P as a partial derivative, right? The derivative for the Lagrangian with respect to Q dot. Remember that? And we can also write down the object or the Hamiltonian for the system, which is some kind of Lagrange transformation of just the PQ dot minus L. Okay? Right? So PQ dot minus L. This is called the Hamiltonian system. So we basically why would you do that? Well, from last time we know that we emphasized somewhat the field theory is about the continuum or infinite degree free. Right? Then you may worry a little bit about is this just trivially generalized to field theory in classical mechanics, which has quite often has finite number of degrees of freedom, or you might worry a little bit, but to convince yourself, you can just treat this continuum field theory in terms of some lattice system. Right? In first lattice, this field theory, you can just pretend, first of all, you can pretend that this is an infinite number degrees of freedom classical mechanics. Okay? Then, by doing that, we can just follow this definition to work out the Hamiltonian, right? I just in order to deal with an infinite number of degrees of freedom system, right? For instance, you can if I lattice my system, this is just trying to set up the picture to build the connection with the picture of classical mechanics. Just for the purpose of trying to work in this picture, and then we will continue to this. Then for this kind of lattice system, you of course do the thing here, right? You can define the conjugate momentum, okay? For each lattice, for instance, okay? For this lattice, okay? You define your P, right? You just treat X as some labeling and we say X. Here's my X. I don't have an X. Write it down. You can treat the X of your index. X just refers to which lattice you work on. Okay? You can just try to now I actually ask the question, I have lattice system. What is the conjugate variables located in some particular X? X will be negative to the index. What is that? this should be, following this definition, some Lagrangian with derivative with respect to phi dot. Phi dot, for phi dot, which phi dot? Of course, the same x, same point, right? Right? We don't want to jump to the other point, right? Now we discrete type, we freedom. If you want to find the conjugate error for a particular position, with the freedom, you should do this. Okay? This phi dot the q dot for the particular x, right, for some point. But L is the total L, okay? L is just a Lagrangian composite, right? Now we can do this. Now you just view this one, you realize that this is nothing but just doing straightforwardly, but this is nothing but everything with respect to phi dot. That means the rate in this total L is an entire integral of the Lagrangian density, for instance. Lagrangian density is also a function of phi, also phi dot. This way, okay? Now, as I said, since I'm now dealing with the lattice system, this integral, the meaning of this continual integral actually becomes a sum, right? So actually here is a sum. Sum over y, all the different y, right? All the different y. See? Now you calculate this one, you immediately realize that only only the y equals the x point contributes, right? So you get the this way, right? Yeah. So maybe to be precise, quantify some volume for each lattice, the volume of each lattice. Now put it here. How you divide the small volume from the left side, you get something called the momentum density. See, momentum is the conjugate of phi, and now it's a good notion to see the density, right, which is given by this model. So indeed, in this way, now now you can, after you get this, you can see after you divide it by the small volume, you can see to take the continuum limit. Okay. The notion of the momentum density is here. It's still true, right? So in this way, there's a good notion about the conjugate momentum, the definition of the conjugate variable. And also we note that I is also a function of x t. Instead, this is defined as derivative of this Lagrangian density with respect to phi dot. This will make that conclusion. If you don't want to do that argument, you can forget it. Okay. Usually, many textbooks just show this definition. Right? Think about it. In a continuous system, we can also define the conjugate variable as some density. Now, surprisingly, all of this setup we can work out in the Hamiltonian. You can either work it in the lattice picture and we continue, or you can just apply it to guess. So obvious that the total Hamiltonian should be integral, a space integral of the Hamiltonian density. Now, in terms of density, Hamiltonian density should be given by the density of P times Q dot minus the Lagrange density and everything. So H is could be space equal, three-dimensional space equal of phi dot minus turning L. And this part is nothing but sometimes we call this Hamiltonian or Hamiltonian. As I said, sometimes we don't distinguish the two, okay? Like the terminology of Lagrangian, okay? Sometimes we use if there's no confusion. So this is the Hamiltonian, which is given by phi dot minus L. Right? Now, this is quite abstract. I just try to clarify in another Hamiltonian language what is the connection between this Lagrangian. Now, you might sometimes get confused. So sometimes I use phi dot, sometimes I use pi. What is the systematic way to understand this dependence? Okay? Dependence for either Lagrangian or Hamiltonian. You still remember? The point is, let me clarify a little bit in order to avoid the confusion. The point is, formally, we should always treat the Hamiltonian as a function of phi and pi. Okay? We treat the phi and pi as independent variables in the Hamiltonian form. You see, here there's no phi dot, which means if you have an expression for your Hamiltonian, there are some places appear some phi dot there to replace by pi. Okay? So we always treat phi and pi as independent variables in the Hamiltonian. On the other hand, for Lagrangian, we think in a different way. Okay? Because in this context, we introduced from the beginning, we don't have conjugated momentum pi as independent variables. We just simply treat the phi and phi dot. Okay? Phi and phi dot are the independent variables. Okay? These are the formal difference for these two. Now it's better to look at some examples in order to understand this game. So let's take one example, which is a simplest field theory for its scalar fields. A simple example is simplest one is a simple free space. Free scalar. For free scalar, the Lagrangian is given by half phi dot square. Now I try to write everything explicitly without any abstract index. Okay. Now this is my Lagrangian. Sometimes you might, from reading the textbooks, you sometimes get some additional minus sign. Quite often, right? Or minus or plus, sometimes confused. So by the way, it's not arbitrary. It's not an arbitrary choice. You can put a minus or plus. It's not like. So what are the rules? What are the rules writing to fix the overall sign? Here, since introduced in last time, we use the metric with the most minus. Okay, most minus sign metric. Convention. Remember that? Also minus. So, as you can see, I always keep this term, the sign for this term is a positive sign. Okay? Following this rule, we can quite clearly explain all the different signs. Which essentially means if they use the contra mu by square locations, sometimes people put a minus sign in front. It's like that. It essentially means to use another metric convention. But the point is, whatever convention notation you use, you should always keep sign in front of this term is called the kinematic term. Okay, to make sure the kinematic energy is positive. So there should be positive sign for this term. Since I use this one, so here you can see. In this way, I write everything in the component, so there's no confusing. But just a bit comment about the convention. So follow this one. As you can see, this is quite a sample Lagrangian, right? Now, if you utilize these two terms, okay? You will get this partial mu by square. Okay? As you can see, the Lorentz index is contracted over. Okay, so this should be Lorentz invariant. So mostly we are focused on this Lorentz invariant theory. This is just coming from symmetry requirement. Of course, you can, if you forget about any symmetry restriction, then you can write a very general forms for your Lagrangian. It's not like that. Because of the symmetry restriction, right? Now, if I want to derive the differential motion for this given Lagrangian, for sure, after a few minutes, you can get this differential motion for this scalar theory. This one, right? It's this one. Sometimes we write it in this way. We just equivalent. Sometimes we even brief, just write a box. Okay? All of these three equations are the same. Just different equations. We need the same thing. Right? Just follow this formula. Follow this formula to get the differential motion. You get this one. Of course, you can check yourself. Are there any questions about the differential motion for classical field? in which term? Yeah, the usual Snoopy argument is say since the field always fall it's 100% away from your interest condition, okay? Which means and those symbolic or whatever you call it, symbolic boundary or infinite far away point is I always need to clear. That's my most Any other question? Some detailed discussion again for how to construct a reasonable series here in the level. Okay. We just mentioned a few, like the series now depends on like double dot, okay? A double dot. And from this example, we also see some symmetry requirements, right? If you want to learn the environment theory, you better to contract over all the learning index in Lagrange. These are the two principles or conditions to construct a reasonable theory. But are they enough, or are there something more? Certainly, there is something more. So one important additional requirement or property of usual reasonable theory is so-called locality. Locality. What is locality? Some of you may already studied it once. I read some textbooks for the context for the QFT. There's also some discussion about locality. But here, you just go back to the very original point where only at this moment we only talk about classic fields. So the point is, even in classical field, there is a notion of locality. It's actually a very simple requirement. One of those. So this is a locality in classical. So what do we mean by locality? What do we mean by locality? We only now, at this moment, only speak ourselves to discuss locality in the context of the classic usage. We're not talking about some common dependent knowledge that we already satisfied about. There will be some non-local notion in our business world. We don't actually about. So in this context, what is locality? Locality, simple requirement says that when you write down or when you obtain your equation motion for your fields, the equation motion should contain only fields. Should contain only fields or derivatives as we at some point see. Equation motion could involve that derivatives at the same point. At the same point. See? In many examples, the equation motion for field is written mathematically in terms of the differential equation, right? And differential operators. So the second order, those equations. But the point is that for local fields, okay, all the equation motions only involve the fields or its derivatives at the same point. Okay? You're not allowed to say, I write down my equation motion, I find my field here equals to my field there, or it's not like that. If you see something like that, it's not local. right? For instance, we already worked out the simple example. There's a box phi plus m squared phi equals 0, right? The point is that for this equation motion or differential equation, you can see trigger is only about the point. I write it this x. Same x, there's no two different positions. This is x and then y. Same point. That's very cool. Right? The meaning of this kind of equation evaluated at the same point means this second derivative of this field at the point x equals to minus m squared times the field value at the same point. Cannot be jumped for distance away. So this is the nature of the locality of this equation motion. Of course, there is an even more familiar example, Maxwell's equation. If you look carefully at the Maxwell equation, see no matter how complicated this equation looks like, or which component of the equation we are looking at, it's all about every term in the single equation should be at the same point. See? There's no equation simultaneously involves two different points. Right? So this is all about the looks like a trivial property of the familiar equations, but you should try to realize that this is nothing but the requirement coming from locality. Or very roughly speaking, locality essentially just means the physical quantity, the value of the physical quantity at this point should be completely determined by his neighborhood, okay? Or surrounding, okay? It's not by something distance away from. This is the locality, right? Now we have more examples. Try to check yourself. For instance, we also have the classic level. We can talk about any example. Even talk about the gravity. So the third example, gravity. License theory. It's okay if you don't know what is Einstein. So to emphasize, write down those theories from some object or dimension. And the Einstein's equation, you check yourself, is also usually the order. The only terms include the second. Talking about the property of impulse. Of course, in this course, we were going to cover another very important equation, which is derived. Equation. This is about some new object where we really introduced this moment. We will do it after a few weeks. Called the spinner. Spinner is also a very fine field. The derived equation associated with this kind of spinner also. Right? So as you can see, in the fundamental level, our current knowledge, the fundamental word in terms of the language of field theory is all about the local time. Right? Now, to be even more clear, by locality, we really mean this Lorentzian density only depends on the values, only depends on, I think I write at some point, okay. So let me write it in the opposite way. So L cannot depend on I'll be waiting this way. Let me do the cutting. I'll be waiting. Not include. For instance, can locality just forbid such kind of terms appear in the function? Something looks like a double integral. Okay. In other words, you also just say that when you write that on management, it should be a single. It should be a single. A generic double integral represents the otherwise, you don't need to do that. So, for instance, such kind of term, if this kind of term appears in a non-linear, indicates this is violate the I'm not saying this kind of theory cannot be defined or it has a trouble. Okay? I'm not saying that way. I'm just saying that in our current knowledge about the fundamental work, there's no such kind of thing. Okay? All about the local. Another comment is, in history, locality is essentially the reason. Okay? It's essentially the reason why we need a field. To go back to history. Right? If people don't realize the locality, everywhere there is locality, maybe we don't need the fields. I'm just go back to history. History, the language of the fields, we can in our mind, simply because we realize the locality is very important. Okay? That's very simple from one direction. For instance, we don't like something incorrect over a long distance immediately, right? We think all the interactions should be involving some propagation. Okay? That's essentially we realize the importance of the locality. So, in this background, we introduce the field. Okay? So locality, in other words, the first reason to bring this concept of the fields. Locality is the reason to introduce fields. Okay, this is the discussion about the locality, which is the important property of classical fields. And next topic, I want to discuss this another perspective. Is the symmetry. Okay, we just mentioned a few, right? A few important properties or requirements to give a reasonable definition for fields, for field theory. Now, the other one is the symmetry, right? we already seen such kind of construction for free fields satisfy this Lorentz invariance. Okay, the Lorentz symmetry. Now we want to discuss more about the symmetry. What happens if a classic field theory includes symmetry? So what are the, apart from the Lorentz symmetry, what are the additional symmetries this Lagrange include or contain? Can you try to observe? Because we want to really stick to, to look at carefully into the symmetry property of the Lagrange. For this theory, what are the more symmetries or even the symmetries? Can you guess? Can you think of try to observe it? We mentioned the Lorentz invariance, right? Lorentz transformation basically include those continuous part and the discrete, some discrete elements, right? But apart from Lorentz, there is another even simple symmetry for this theory. What is that? Sorry? Scale. No, okay, scale. No, that's not what I want. It's an even simple one. What is that? That's right. It's a Z2. Okay. What are the Z2 symmetry here? So if you do the transformation, see, phi goes to minus phi. This is invariant, you see? Because all the terms are the quadratic, right? All the terms are quadratic. We have 2 phi, phi times phi. Phi goes to minus phi. This is too simple, right? Too simple to observe. Yeah, but that's the direction we want to explore. To seriously look into this symmetry. So this is the next topic I want to discuss, which is about symmetry. And yeah, this is about symmetry. Again, we haven't yet discussed quantization fields at this moment. All these property discussion is looking at the classic level. There's a lot of fields here. That's level. Now, consider, for example, a continuous transformation on the field phi. Before we do anything, we first should make it very clear. What is the definition of a symmetry, right? When you talk about symmetry, it's better to make it very clear. What do you mean by that? What do you mean by a symmetry? In other words, for which kind of properties of a given theory we call there is a symmetry. Okay? So make it very clear. So consider continuous transformation of the field phi. We can always write it in a infinitesimal form, right? Which which looks phi x transform. Okay? When we see transformation, always transform from A to B. Okay? In order to avoid any confusion. Okay? We always see transform from A to B. A is the object before transformation, B is the object after transformation. The error means send this guy before transformation to the guy after transformation. Okay? Well, this equation needs a little bit of thinking, okay? It's not obviously you can just understand what the meaning of this one, but it can be explained, okay? So when we see, okay, sometimes we mix up the different concepts like coordinate transformation or transformation of the fields, or infinitesimal transformation, or that the transformation I want to use is from A to B with an error, okay, in the middle. I like the last language, and because that can avoid many confusions. Okay? Here, think about the given field. Picture-wise, when people say, okay, I have a field composition means in some coordinate, right? Or some function, for instance, mathematics, right? It's the same function. Now, let's talk about the transformation. Let's talk about the transformation. One thing you can talk about is I do a coordinate transformation. Okay? What do you mean by coordinate transformation? We know coordinate transformation is just start from one coordinate. Okay? One coordinate with the origin, for example. You switch to another coordinate. Okay? But from our experience, we already understood that kind of transformation is not that physical. Okay? We don't want to confuse ourselves, so we don't use that component to see, okay, I do coordinate transformation. Always abandon those components. Okay? Now we switch to the new one, better one, physical one, okay? Or more sharper one, okay? Whenever we see transformation, will always need to transform the fields. Okay? Let me read the example. I want to translate, okay? Translate the field, okay? Or rotate. We already learned last time the whole Lorentz transformation, including rotations, right? Now, don't forget there are also 4 different translations. I can translate along time vector x, y, and z. With these 4 additional translations, together with the previous Lorentz transformation, they form the entire transfer group. We don't do that language discussion. Just to try to emphasize, there is a very simple transformation which is called a translation. Okay? Translation is a move, translate from A to B. Now, I want to translate my field. Okay? In this picture, you see, which means for this field that I want to translate. I want to translate. Okay, to another field. Okay, visualize it into also try to create the story. Okay, now again, so that's my learning to here. Now this is a better way to understand the transformation of the field. I don't want to confuse myself to bring up the concept of the coordinate transformation. Right? So from now, again, let me emphasize. Whenever I see transformation, I mean transform the fields. Rotate my field, translate my fields, whatever. It's all about my fields. Okay. Now, with that terminology, you can easily understand this equation. Okay. Because this is the infinitesimal transformation. After transformation, the new field, which I denoted here, the phi prime, should always evolve the original fields plus some little amount. See, this is the infinitesimal transformation. maybe you do a little bit change, okay? Pivot to some small parameter, alpha. Alpha is very small. This is a small. Okay? Together with some particular operation, I use very schematically labeled with the delta. Delta can mean many, many different things. Can be a first derivative or a combination of derivative, can be just many different things. This is understandable, right? This equation just means after transformation, the new fields, how to connect new fields with the original fields, we should connect it in this way with some particular here. I didn't specify the operator. That's it. Because this is a mathematical transformation. Right? It's not surprising because we already learned from the previous course. If you always prepare extension like that, deconstruct a change into very small pieces. So if I only concern a very small, tiny transformation, I can always express it in this way. So this is important to emphasize. So alpha here is a infinitesimal parameter. And the third kind is information, for example, the same thing. Yeah, this looks a little bit abstract. We will come to a concrete example very soon. Okay? Then we have better understanding. Now, this is only about a small or infinitesimal change or transform of this field phi. It's not yet enough to define the symmetry. What do we mean by symmetry? A symmetry is about if such kind of transformation leads the action invariant. We call that this is a symmetry. Okay. Now there are two important ingredients in this definition of symmetry. Right? First of all, we try to bring up this form of the infinitesimal transformation. This is only possible about if your symmetry is continuous. Okay, you see, it's obvious, right? Because there's a small parameter. The parameter is a continuous parameter. See, so discrete, like the parity and the time reversal we introduced last time, is impossible to do in that way. Okay, because it's completely different type. Here we more focus more on this continuous type of the symmetry. That's why we can write down an infinitesimal version of a transformation of a field, and above on that, make the definition for a symmetry. If under those transformations, if the action is invariant, we call such transformation defines a symmetry. Because there is something invariant, right? As you can feel, in the very beginning we emphasized, whenever we talk about the symmetry, you should make it very clear which object is invariant, okay? Now here it comes back to here. In the context of the field theory, the definition of the symmetry is given in this way. Okay? Now, so what is the consequence if the action is invariant? What is the big deal if I find that my action is invariant? I think this is better to be in the... Yeah, let's have a break.